Hi there, this is Fritz Rinker. I was working on a brain model based on different principles than the current large language models, and now I see the discussion about reasoning in large language models and that they cannot reason. I think that's a fair assessment of it. Basically, the mistake that large language models have to make is that they go back to the logic positivism, a kind of fallacy that was prevalent in philosophy in the, I think, 1900, in the beginning of it, like 1920, when people discovered logic, and then they thought, well, we can make a logic inference of everything that is true. Let's say if I have a cup and it's on the table, then the cup doesn't fall from the table, and I make logic symbols, and then I do kind of mathematic kind of operations on those symbols, and as a result, I get the outcome. And that's also the basis of the early expert systems that were made with computers, and of course mathematics in principle. If you have measures of stuff, then you can make calculations with them, and that's mathematics. But they quickly found out that that's not the way logic works. Logic is a special case. It's basically behavioral implementation of whatever you perceive, and or let's say, if I want to explain it really short, it's like the motor system. Once you can only do a few actions with your body, but you have to figure out which one in which sequence. So it's not really super subtle. You pick something up, you put it down, you shift it one place to the other, and those are really quite crude manipulations. But there's quite a few. There's not very much, let's say. But to pick the right one, you have to go through a whole process of figuring out what you see, what's the situation, if this whatever apple you're trying to eat is rotten or not, if it's where you're walking, all these very complicated, very nuanced things. And in the brain, they're not. There's no system that has like switches on and off to tell you if you're on the ledge or not, or if you're too close or not, or if the apple is rotten or not, or if it's a bee or it's a wasp or it's a hornet. There's no switches. That's the delicate fuzzy logic system, which was then the next step in the evolution of machine learning, or you could say signal processing, to fix those kind of problems with logic. And in the end, you get the insight, and of course also direct knowledge of spikes in the brain and spikes in the sensory system, and then you have rate coding, and you have more or less you have different coding schemes in the neurons, which I think are misinterpreted at the moment. Hence my model, but large language models never get to that because they go with annotated visual input and words. And words are logic. Words are logic elements. And I explained in the previous video that it's very strange approach to try to eke out the nuances in meaning between words by just using a lot of words. It's like if I wanted to explain the difference between a rhino and an elephant, then rhino has a tusk and an elephant has a snout, or whatever you call that, slurf. What's a slurf? Well, that's just a long thing. It's like, but a tusk is also a long, can be pointy. Slurf is not pointy. Well, it's a little bit pointy, etc., etc. But then, you have still no knowledge about what it looks like. It's gray. Okay, it's gray, and it has lots of muscles, like for an elephant. But tusk has no muscles. It's basically hair. It's chitin or something like that. Etc., etc. And you could go on, and then, okay, what is gray? It's gray slurf. Okay, right. What's gray? I have no idea what's gray. Elephants are gray and rhinos are gray. But what is gray? I have no idea. That could be equivalent to actual strawberry structure. So in the imagination of a person you explain it to that never ever seen a rhino or an elephant, the imagination could produce a kind of large animal with a skin made out of strawberries. That's possible because you're trying to get it out of the words and it's not in the words. So reasoning, of course, will also have the same problem, that any word that you use, like strawberry, for instance, doesn't have any other meaning than that it's different from a word like raspberry or tomato. That's the only thing that you know about strawberry if you are a large language model and you get presented with the words. And then you can say, well, strawberries are plants. Well, raspberries are plants too, so there's no difference. Oh, yeah, but strawberries are red, and raspberries can be red and blue or something like that. I don't know, purple. Oh, there's slight difference, but you have to pick that up, etc., etc., etc. And then in the end, is it ever explained that strawberries is like a conical thing, and that the raspberry is, I hope I used the word right because maybe I have to look it up, but it's it's like a bunch of grapes. What are grapes? I've never seen grapes. Large language model doesn't know. And then you can show it a picture, and then you say these are grapes. Okay, so then that whole structure there with the bulbous things is grapes, and this is a grape, single. Okay, so this is one of those bulbs. Okay, well that's just so different from how the brain does it, because the brain never had grapes until somebody called them grapes. They just had the thing, and it could find the thing. This is very interesting about like say the sensory field of a spiking sensory network, is that it doesn't matter how you configure the neurons as long as it can distinguish between things, which is a very fundamental logic, like obvious thing, is that you don't have to have a neuron that is specific for black bears or brown bears. You just have to make sure that you can keep them, tell them apart and know which one you have to run for your life or climb into a tree or lie down dead. It's the discrimination, which is convenient because that's also basically all you can do as a information processing intelligent system, is to distinguish. Large language models cannot distinguish very much, except when you present it with different words in different contexts. And that's, let's say, for large language models which don't have visual or multimodal, as they call it, but that's a bit rich. So what happens when we reason is that we go okay, so the cup is on the table, and then we have to know a lot about the table and about what is a cup, and about the fact that you have normal force and all these things. But those are like, so what you discover is that once you try to make logic work, you have to put a lot of things that are already there in your mind, already understood about the behavior of things, into some kind of language form, so that it can interact in the logical let's say what you call it, medium, or what you call it, logical context. And if you don't, then it cannot, and then your logic produces results that are wrong, and the brain doesn't. So, and large language models just don't have all that context. They don't have the raw input, so they cannot. So, but because what happens in the brain is that if you say, okay, can the cup sink through the table? We have to understand what sinking is, and that's, let's say, and what tables are like. But what happens in your brain is that you try to imagine it, and then you go back to the elements that you perceive, the experience that you had in your life of tables and cups, and maybe some kind of rules that somebody dictated. Those are also experiences. Somebody says, no, your cup cannot sink through a table. If you have that experience, then you can directly say, no, I know. It's impossible. But if you don't, then you have to kind of imagine it. And you can no, tables are really hard. I try to, I can lean on a table. I can put all kinds of heavy stuff on tables. Wood. I'm here sitting here next to an oak table. Is hard. I cannot imagine, like it might, but I cannot imagine that happening. So that's basically all I have, is that I cannot imagine it, and now I think it's not true. So you cannot, so a cop cannot sink through a table just like that. Luckily, otherwise my coffee would be ruined. But bottom line is that a large language model cannot do that because it doesn't have the space that it can get its attention to in order to resolve the question. It cannot go into the, let's say, the reverie or the daydreaming or the hallucination that I just did about reality and my experiences with reality, because it doesn't have any experiences with reality. So that's where the weakness of large language models and reasoning comes from. And there's a chance that androids, robots, change that. But that really depends on how they are perceiving the world. So, let's say if you try to, let's say, so if they have a low grain, or I'm not sure which one is better, low grain, high grain, but if they have a very basic level of perceiving, then they can, and they have the right neural system, which they don't at the moment, then they might be able to go back and research that and let that help them determine some fact about reality that they are questioned about. So then the robot is sitting next to a table and it's leaning on the table, and then it's asked, do you think that the cup can sink, this cup of coffee can sink through the table? And then the robot has to kind of contemplate because it probably doesn't have a rule about cups. And then so it has to look at the cup. So no, the cup is on the table supports the cup, and I can touch the table. It's hard, and the cup is hard. And hard things don't slide into each other, whatever. And so I don't think that's possible. I never seen it happen. No, it's impossible. That's the difference. So robots are more likely, much more likely, and to be able to reason, truly reason. And of course you can say, well, no, but there's, and or to qualify, there's just a space of questions that a large language model can reason about, especially when it's logic. Then it might be able to reason perfectly. That just depends on the knowledge it has. And then there's of course a realm where it's mixed, where you can say, well, it can reason because it has part of the knowledge, and that's enough to reach the correct conclusions. But it cannot reason like a human being because it doesn't have the experience and the depth of knowledge and experience as a human being. And let's say, to conclude this commentary or something like, it's like humans also have massive problems with reasoning. I mean, the whole political debate is about discussing topics that if you could reason clearly with experience, so that's the big hole in the experience. Like people that, if you are a border control guy in Mexico or something like that, and you see or if you're handling immigrants and you know the actual numbers, then you just draw different conclusions, and you have different policies, like all these sanctuary cities, New York and stuff like that. They gave up on trying to arrest immigrants because it just leads to them being driven into prostitution and crime, and you don't want crime in your city. So then you have to just allow them to be there, and that's just totally misunderstood because the facts are not there, the experiences are not there, and people are like sitting in their homes and thinking, oh, these are all rapists, which is a very nice, like very popular theme to assume that every man outside your home is a rapist. That keeps people in front of the television and stuck to the couch and eating and inside and unexperienced. But so we have massive problems with that in real life with humans. So you can imagine that large language model that never gets out of the box has the same challenges. And I think it can only be resolved by giving them a body, letting them work, run around and walk around, and of course using a different kind of neural system that I'm working on. which is just the final one. I used to be a neuroscientist, so that's why I have an opinion about this. I hope you